So now we move on to sinusoidal voltage and current values. Okay, in this section we're going to look at the differences between an instantaneous value, which can occur anywhere along the sinusoidal plot on that sine wave. We're going to find the peak values, the peak-to-peak values. Then we're going to start determining and defining some other relationships and measurements. First one being RMS, or the root mean square relationship, which is going to require a calculation that we're going to find. And then we're going to explain the average value as always zero over a complete cycle. And we're going to see basically that uses to really do a little bit of calculus, but the average value across a sine wave is zero. And then we're going to find the half cycle average value. So we're going to go ahead and go through. I want to try to keep track of my time here and keep these a little shorter. So, sinusoidal voltage and current values. So we look at first the instantaneous values. When you look at the plot of a sine wave, the sine wave is actually made up of an infinite number of points on that sine wave. And if you picked a point anywhere on there, you would have to calculate using the sine or cosine relationship of the maximum value for the sine wave, and it would give you then the instantaneous value. And that instantaneous value is a relationship with time. Okay, look at the plots here on these two graphs. The first one is time undefined. We could say it was in seconds. The second one is in time in microseconds, 10 to the minus 6 of a second. So we're going to be able to use those. Again, pull out your notebook, keep track of these metric relationships. So in looking at the instantaneous value, the illustration then below says that any point in time on a sine wave, voltage or current, has an instantaneous value. And we're going to see how to calculate that. This instantaneous value is different at different points along the curve. So you can see, if you look at here on this first one where they're not really defined, voltage 1, voltage 2, voltage 3 on the vertical axis, time 1, time 2, time 3 on the horizontal axis. Instantaneous values are positive during the positive alternation and negative during the negative alternation. Instantaneous values of voltage and current then are symbolized by a lowercase v and I. In your 131 course, you were probably used to using capital letters, capital V, capital I for current, capital R for resistance. Now we have to start using a lowercase letter, and typically that lowercase letter has a parenthetical expression behind it identifying the measure, in this case in seconds along the horizontal axis, in volts, microvolts or millivolts in the vertical. The curve in part A shows voltage only but applies equally to current. Voltage only but applies only to current, where the V's are replaced with I's. Okay, so all of those V's would become I's. An example then of an instantaneous value in part B makes all of the voltage measurements. Notice we've got a capital V here for the values, and then a microsecond value on the horizontal axis. So 7.07 volts, if we look here, gives us a time measurement that occurs at 2.5 microseconds. So at 2.5 microseconds into this propagation of the waveform gives us a maximum value, or an instantaneous value on the plot, of 7.07 volts. Okay, you can also think of it as a percentage. This is 70.07% of the way up to the maximum, which would be 10. If I take 70.7% of 10, I get 70.07. 10 volts at 5 microseconds, 0 volts at 10 microseconds because it's going back down, and so on. So those are our instantaneous values. Pull out your notebook, write some notes to yourself so that you understand what that instantaneous value is telling you. Now the peak value, well, in this case over here on the left, the peak value was that 10. So for any value of peak on a sinusoid, we can identify that value as V sub P, or V peak. The peak value of a sine wave is the value of the voltage or current at the positive or negative maximum or peak with respect to zero. Remember, zero is on the horizontal. Since the positive and negative peak values are equal in magnitude, a sine wave is characterized by a single peak value. Sometimes we would calculate this as peak value plus or minus, okay, depending on how you want to represent and what value you needed. The peak value then we also call the amplitude of this sinusoid. If we want to look at the distance between the negative peak and the positive peak, we now have something called the peak to peak value. Peak to peak value of a sine wave, as shown here, is identified as V sub pp. So notice the mathematical relationship says that V sub pp is equal to nothing more than twice Vp, or twice Ip if we're doing the current peak to peak. RMS. Our RMS value is a little different because we have to calculate that with respect to some value or some meaning. The term RMS stands for the root mean square. Most AC voltages display RMS voltage. So our voltmeters that you'll use in your lab, most of them are going to display your values in RMS. Some of them do it in average. Only on your oscilloscope will you do the instantaneous value. So the 120 volt at your outlet, on your wall outlet, is 120 volts RMS, root mean square. The RMS value is also referred to as the effective value of a sinusoidal voltage. That's actually a measure of the heating effect of a sine wave, and we'll look at that a little bit. These two relationships show you how a DC relationship relates to an AC relationship in RMS, and the calculating effectiveness is based upon the same amount of heat that would be measured and calculated between a given resistor of resistor value between an RMS calculated value or an AC signal going through that that resistor. So RMS, root mean square, that's telling us you're going to take the square root of the average value and square it, okay? So the RMS value of a sinusoidal voltage is equal to the DC voltage that produces the same amount of heat in a resistance as does a sinusoidal voltage. So to do this by using this measurement would be too cumbersome, okay? By trying to calculate an AC and a DC and using a thermometer and whatever. So we can do this mathematically. Mathematically, volts RMS is 70%, 0.707 of the peak value. The same thing applies with the current. So using these relationships, then I can move my terms around to calculate for the peak value. I just divide through by 0.707 on both sides, and the peak value is 0.707 of the RMS value, okay, which gives us here 1.414 times V RMS. The same thing would apply mathematically for our peak to peak value, but in this case, since it's twice, remember we said back here that the value was twice the voltage or the current. So in this case, 2 times 1.414 gives us or 2.828 in each of these. So if we want to calculate then this value, then all we have to do is enter the RMS value or the peak value, and we can use that relationship to calculate one for the other. So we also identified something known as the average value. The average value then is a sine wave taken over one complete cycle, and it's always zero because of the positive value and the negative value offset, and they cancel each other. So if we again would have to do a little bit of calculus to calculate how this is done, the mathematical relationship, and if you look in the back of your book in the appendix, it'll show you how this is calculated. The average value is 2 times pi. Always use the pi key on your calculator instead of 3.14 blah 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 times the peak value. Or we can do the relationship that says the average is equal to, I gotta turn my timer off here, is equal to 0.637 times the peak value. And so if we take a look at this relationship, this example, determine V peak, peak to peak, VRMS, and the half cycle average for this sine wave. You can see we've just run our values through here. 2 times the peak. Well, the peak here was 4.5. 2 times 4.5 gives us 9 volts. The RMS value, 70%, 7.07 times that gives us 3.18, and the average value, 6.37 times the peak, gives us 2.87. So in every case, you see the value is different. What becomes important here is understanding how, when you're using your equipment, your voltmeter or your oscilloscope, what you're actually seeing and what you are actually measuring. Because if not, you will end up with the wrong value of voltage that you need to use. Okay, so when we come back, we're going to take a look at the angular measurement of a sine wave.